Hi, good evening. My name is Stephen Benjamin. I'm going to be presenting my final project for CSCI E-92 operating systems. My operating system name is SaintOS. It's written for the Freescale K70 tower platform, which features a 32-bit ARM Cortex M4 processor. It has support for a number of devices on the tower, such as the LEDs, LCD screen, some capacitive touchpads, push buttons, potentiometer, and so forth. It has an in-memory file system. Many aspects of the OS are POSIX-like. It's a multi-user operating system, full support for user and group-based identities, and I use the M4's cryptographic acceleration unit to do SHA-256 hashing for passwords. I also have support for basic semaphores. When the system first boots, it goes through a number of steps. It runs MCG init for the master clock generator, initializes the SD-RAM, creates our first memory block for malloc, initializes the file system, any devices. It creates the first user, which would be root, and that has a simple password of change.me, which can be changed later. And then it initializes some of the clocks I'm going to be using. Flex timer 0, FTM 0, is used to keep a 1 millisecond tick for the date. And the systig timer is used as a quantum for a scheduler, and it is configured for 50 milliseconds. Once all of this is done, I call priv unprivileged to enter unprivileged mode and spawn the first initial process, initd. Initd spawns some additional processes. It starts login prompts on UART2, UART3, and UART4. It also runs a little message of the day program, so something is displayed to the LCD screen. And then it sets watchers on the initial processes. If they die, they get respawned. Watch calls a function when a process exits. It's kind of like a non-blocking wait, so someone can watch more than one process at once. Let's actually go ahead and run the operating system from within KDS. We can start it. You'll see a little message of the day printing some ASCII art to the LCD screen. And if I go to my terminal window, I have 3 instances of Minicom open, connected to each of the 3 UART devices. And let's go ahead and log in. When I log in, I get a prompt. I can run ps and see the various processes. The init daemon, ps of course, is the one that's running, and the 3 login shells, and then the shell, the interactive shell that I'm logged into now. I can add a user. Let's add a user called Bob, and log him in over on this UART in the upper right corner. If I do a ps again, I'll see that Bob is now running a shell. I can use the kill command to kill his shell. I can do ls to see a listing of all the files. Every device is a file. I run stat. For example, on the LCD device, I can see that its major is 0, its minor is 0, the day it was created, modified, its permissions, the owner, and the group. I can create my own file called foo. If I do stat on foo, I can see it's owned by me, its group is me, and then the mode. I can do chmod, make the file readable and writable only by me. If Bob tries to stat foo, he's going to get permission denied. If I come over here, I can chown, change ownership of the file to Bob for foo, and then Bob will be able to stat the file. Commands are also protected by the permission system. While Bob is able to see the date, he can't set the date. He's going to get a permission denied. But if I come over here and do it as root, I can set the clock to the current time. The time is tracked as the number of milliseconds since January 1st, 1970. After I run this, I can see that the time is now correct, and Bob can see this time as well. There's other commands, for example, that Bob can't see. LSOF shows all of the open files on the system. If Bob tries to do that, he will not be permitted to do that. The permission system for SaintOS is modeled after the Unix permission system. If I do stat again on foo, you can see this mode. The mode is represented as read, write, or execute for 3 different scopes for the owner, the group, or the world. It's given as an octal number typically. So for example, 777 has all of the bits set, which means everyone can read, write, or execute regardless of whether they're the owner, group, or world. Alternatively, I can set something like 644, so only the owner can write to a file, but the world or the group can read to it. So the current permissions of the foo file only allow the owner to read, write, or execute, but I can change that to allow the group to read the file. So if I set 740 on foo, you'll see that the owner can read, write, or execute, and the group is allowed to read. So let's add a new group called foo, and let's change the group of the file to foo. So we can see that the group is updated, and let's add a new user called Sally, and let's add her to the group foo. So when Sally logs in, she's actually able to read the foo file, but if she tries to write to it, she's not going to be allowed to. If we remove her from the group foo, she'll again be denied access to the file. The OS also has a couple of other interesting features. For example, there's an implementation of STTY, which is very similar to what you might find on a Unix system. It controls various echo options if characters are echoed back to the user, or if control characters are echoed back with the caret notation. So for example, the program ser2lcd, which is writing some output to the LCD screen. When I hit Control D, you'll see that the character is echoed back to the user. I can also turn off echo in general, and if I type, nothing is echoed back. I make use of this when a user logs in and the password prompt is displayed, echo is turned off, so no one can read their password who's overlooking their shoulder. There's also options for how we handle carriage returns and new lines. So if your terminal program sends a carriage return, if ICRNL is set, it will convert that to a new line. And on output, if your program only sends a new line, for most terminal programs, you want to send a new line plus carriage return. So STTY can take care of that. My operating system also has support for basic semaphores. I found as I was developing the OS that there's a lot of critical regions where a context switch occurring and potentially another program trying to perform the same operation or a similar operation could cause corruption. For example, if malloc is in the process of operating on the linked list where I might be resizing a memory block and two processes are trying to do this at the same time, that would be a bad thing. My initial approach was to wrap these critical regions themselves within disable and enable interrupts instructions. And that works fine, but what ends up happening is the OS spends a lot of time with interrupts disabled, especially since the user system and the group system consist of linked lists, which are critical regions. I ended up implementing a basic semaphore. The semaphores are not using the load or store exclusive instructions from ARM. Hopefully I can try to get that working by Friday, but for right now, the semaphores are still based on disable, enable, but you're spending a much shorter time in that space because it's using that to get a lock. So I have a couple of demo programs. For example, there's one called semdemo. What happens is the program obtains a lock, it emulates doing some work, and then it releases it. So if I start it multiple times, you'll see that the processes are handing the semaphore back and forth. I can run it a third time, and you'll see that the processes are all playing nicely, handing the semaphore back and forth between each other. The semaphores are implemented as a struct that contains the count of the resources available, how many are currently available, and then a circular buffer of PIDs waiting on the semaphore. And then there's three functions that a user can call. Seminit initializes the semaphore with a particular count. Semdown tries to obtain the semaphore. If it fails, if there's nothing available, then the process will be blocked. And then semup returns the semaphore, returns a resource to the queue. And then if there's a process waiting, it is woken up. A more realistic demo of how the semaphores might be used is to aggregate data from multiple processes into a single stream. So I have two little sample programs, one that's reading the capacitive touchpad that sits over one of the LEDs and it's going to write it to a file. And then I have another program that's going to read the potentiometer and write it to a file. These programs are aware of semaphores. The first option is whether semaphores are going to be, whether the semaphore is going to be used or not. So I'm going to say off for the first attempt, and then I'm going to write both results to this file called readings. It's going to take 1,000 readings. Both of them are going to run at the same time and write the results. What you're going to see happen is, because the two processes are running, context switches are happening, and there's no control over who's writing to the file at what time, that there's quite a bit of interleaving. You'll see that there's corruption, places where mistakes happen like this, you see that there's corruption in the file. But when I coordinate with the semaphores, let's remove this file and let's start again. This time the semaphore is turned on. You're going to see that it takes slightly longer, but the two programs are handing the semaphore back and forth, so that only one process is writing to a file at a time, and you'll see that this file is corruption-free. And that's it. Thank you.